My name is Evan Olson, and I'll be solving problem 6.59 from Fundamentals of Heat and Mass Transfer, 8th edition. So the problem statement says that we have dry air at 32 degrees Celsius flowing over a wetted plate of 0.25 square meter area, and that the average convection coefficient is 22 watts per meter squared Kelvin over that surface area. Um, and since it's at a constant temperature, the heater power required to maintain that temperature of 27 degrees Celsius is 498 watts. We need to estimate the power required to maintain the wetted plate at a temperature of 42 degrees Celsius with dry air flowing over it at the same bulk temperature if the convection coefficients remain the same. So this is our schematic for the problem. We have our wetted plate with 0.25 square meter area, and we have our dry air flowing over the surface with a bulk temperature of 32 degrees Celsius and a average convection coefficient of 22 watts per meter squared Kelvin. Uh, these are the values that are tabulated in the problem. We have at 27 degrees Celsius isothermal plate temperature, we require a heater power of 498 watts, and we need to find what the heater power will be if we wanted to have a constant plate temperature of 42 degrees Celsius. In order to find that wattage, we first need to find what the evaporative heat transfer rate is. Since this is at steady state, we know that our heat generated is going to be equal to our heat transfer due to convection plus our heat transfer due to the fluid evaporating, in this case, water. And for 27 degrees Celsius, we know we can easily find our heat transfer due to convection since we know all of these terms. It will just be our convection coefficient times our surface area times that delta T. And that gives us 27.5 watts, which is traveling into the plate since the surface temperature is 27 degrees Celsius and the air temperature is 32 degrees Celsius. That's going to create a temperature gradient pushing heat into the plate. So that's going to help us in this case. We can next find what our evaporative heat transfer rate is, and that just takes our generated heat minus our heat transfer due to convection. And we know this 498 watts since it was given in the problem statement. So that means we know that the evaporative heat transfer rate is going to have to be equal to 470.5 watts. Evaporative heat transfer is defined as the mass flow rate of evaporation times the latent heat of vaporization of the fluid that we're working with. And we know that for water at around these conditions, it's 2.45 times 10 to the 6 joules per kilogram. And if we plug in those numbers there and rearrange to solve for our m dot of evaporation for the 27 degrees Celsius case, we find that it is around 1.92 times 10 to the minus 4 kilograms per second. We can then relate that to our 42 degrees Celsius isothermal plate by relating the mass transfer between the two. We know that the mass transfer rate is going to be proportional to the difference in vapor pressures at the two different surface temperatures. And so if we find our saturation vapor pressures of water vapor at our two surface or our two plate temperatures at 27 Celsius and 42 Celsius, we can see that there's quite a big difference here. And our evaporation rate is going to be proportional to our evaporation rate at 27 Celsius times the ratio between our vapor pressures. And if we do this calculation, plugging in our numbers, we get an evaporation rate of 4.42 times 10 to the minus 4, which is about double, or a little bit more than double the first case. And then this allows us to pretty easily solve for our our evaporation heat transfer rate for the 42 Celsius plate by just using the same relationship, which is m dot evap at 42 Celsius times our latent heat of vaporization, which will be a little bit different, just taken at 42 Celsius instead of 27 Celsius. And then we get that our evaporation heat transfer rate needs to be 1063.89 watts. And then we're able to calculate our convection or our heat transfer due to convection at 42 degrees Celsius as well. We know that our convection coefficient is going to remain constant since that was given in the problem statement. And we know our area is remaining the same. The only thing that's changing here is our surface temperature. And so this turns from being a 10 Kelvin difference to a negative 10 Kelvin difference. So there's going to be 27.5 watts flowing out of our plate, since our plate is going to be hotter than the bulk fluid flowing over it. And then we can simply calculate the required heat input to the system to keep that isothermal plate, which is just going to be our heat transfer due to convection plus our evaporation heat transfer, and that will be 27.5 watts negative plus 1063 watts, which gives us a final answer of 1036.39 watts.